Hello.
Hello.
Hello, Larnie.
Hello.
Good morning. I'm
Good
sorry.
morning.
So I think it's time to start a meeting. So all invited guests have been arrived. Okay, let's start our meeting. But before we begin our lecture series, please be informed that all participants are kindly requested to mute the microphone during talk session. Good morning, everyone. Welcome to Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada, Yogyakarta. Let me introduce myself. My name is Made Beni Prastawiranata. I will be the moderator for today's lecture. Distinguished guest participant, ladies and gentlemen. First, let us welcome our special invited guests to spare their valuable time to make this event so meaningful for us. Distinguished speaker, Professor Indah Emilia Wijayanti, the chair of Algebra Laboratory, and also the chair of organizing committee for this lecture series. And distinguished speaker, Professor Lani Betran Natividad, PhD, and all participants for today's lecture series. This event are supported by Indonesian Mathematical Society and Indonesian Algebra Society. So ladies and gentlemen, welcome to the second lecture series on algebraic quantum mechanics. Now let us give the overview of the event. The main agenda consists of two sessions of lecture. The first session will be delivered by Professor Larni Beltran, and the second one will be delivered by Professor Indah Emilia. After those lectures, we will have photo session, announcement, and closing. So ladies and gentlemen, to begin our first lecture, I would like to introduce our first speaker. I will share my screen. Can you see my screen?
Yes.
Okay. So the first speaker, Larni Beltran Natividad, PhD. She is associate professor at St. Louis University. She got bachelor degree in St. Louis University, Baguio City, and continue her master in University of Philippines, Baguio City, and finally get the PhD at Ateneo de Manila University, Philippines, with dissertation titles, symbols correspondence for Euclidean system, with supervision by Professor Job and Nabli. And she got two recent publications. The first one titled Star Product on the Euclidean Motion Group, and the second one, Star Product on Euclidean Motion Group on the plane. Okay. So before we start, to participants who have a question, please write it down in the chat, or will be directly allowed to ask during Q&A session. We have an hour for each lecture, including Q&A part. Now we would like to invite Professor Larni to start the lecture. The lecture title, Wigner-Weil Formalism on Lie group. To Professor Larni, please.
Thank you, sir. Thank you for that introduction, sir. And I'm going to share my screen now. Wait for a while. Yeah. Can you see my screen? Can you hear me?
Yes. Yeah.
Okay. So, thank you, sir, again for the introduction. And today I'm going to share to you the results of our project. Okay, with my advisor, Dr. Job Nable of Ateneo de Manila University, and I hope he's with us today. I do not know if he's with us today. And I want to acknowledge also the presence of my group mates. I think Sir Alex is here with us. And um, my work is entitled The Wiener-Weil Formalism on Ali Groups. Okay? So this one is the flow of my discussion. And I want to start this by recalling again the mathematical structures of the three areas in physics, specifically classical mechanics. We have standard quantum mechanics, and then our focus today is on phase-space quantum mechanics that makes this standard quantum mechanics similar to that of classical mechanics. Okay, so let's start first with the states of the system. So the states of the system under classical mechanics are completely defined by points in 2n-dimensional space. And also, under standard quantum mechanics, the states would now be the vectors in Hilbert space. And under phase-space quantum mechanics, the states are just the same as in the classical mechanics. And for our observables here, these are the objects that we want to measure. Okay, so under classical mechanics, we have here the smooth functions f on phase space. And under standard quantum mechanics, our observables are self-adjoint linear operators. And later in our discussion, we will call this as the Vial transform. And under phase-space quantum mechanics, our observables here are, we have distribution functions, and later we will call this as the Wiener function. And in order to measure these observables under classical mechanics, we're going to evaluate the function f at QP. And under standard quantum mechanics, we're going to compute the expected value in terms of the self-adjoint linear operators. And under phase-space quantum mechanics, we're going to compute the expected value in terms of the distribution function. And also, we have to consider here the evolution of the system. So under classical mechanics, this one is generated by time-dependent Hamilton's equation. And under standard quantum mechanics, this one actually under Schrodinger equation. And under phase-space quantum mechanics, the evolution is specified by Moyal's equation. And as I have said, our focus is on phase-space quantum mechanics. So we're going to consider here the three objects. We have the Vial transform, the Wiener function, and we also have here the star product of functions on phase space. Okay, so let's consider the first object. We have here the Vial transform. Let's consider the Vial quantization recipe formulated by Hermann Weyl in 1927 that shows how operators are assigned to functions. So we're given here classical phase space function written in its Fourier expansion, and we can quantize this by replacing the variables q and p by operators q hat and p hat in order to obtain this linear operator associated with the phase space function sigma. And we call this as the Vial transform. Okay, so we can rewrite this Vial transform in terms of the Fourier transform of the function sigma, and also here we have the unitary representation. But in the case of Heisenberg Weyl group, we have here rho, okay, which represents the Schrodinger representation. Okay, so this Weyl transform can be mapped to another function, and we call this as the Wiener transform. And according to Grunwald and Moyal, these two are inverse processes of each other. Okay, so another object is the Wiener function, and we know that quantum mechanics is actually statistical in nature. So before we consider the quantum case, let's consider first the probability distribution in the classical case. So here, we need to consider the characteristic function of a random variable x. So this one is given by this equation, which is actually the expectation value of e raised to itx. And this characteristic function can be written as a Fourier transform of the probability density function f sub t. And using this time, the inverse Fourier transform, we can recover the probability density function in terms of the characteristic function phi. And we want this object also in quantum case. Okay, so instead of using this random variable x, I will now be using this pair of variables q and p. So the characteristic function associated to the pair of random variables would now be this equation. And this time, I will let t sub 1 be equal to negative u and t sub 2 be equal to v, and replacing again q and p by the operators q hat and p hat, we already have here what we call the Vial operator. And the characteristic function associated to the pair of variables q hat and p hat is now represented by w tilde, which is the expected value of the Vial operator given this pure state rho hat. And again, using the concept of Fourier transform and inverse Fourier transform, we can now have the probability density function given by this equation in terms of the characteristic function w tilde that will represent the probability distribution in the quantum case. Okay, so this probability distribution in the quantum case is just like the same or similar to the probability distribution that we know. But we have here additional property that there are regions wherein we have negative probability. So this one is properly termed as quasi-probability distribution. Okay. So in 1932, Eugene Wiener formulated this quasi-probability function when he studied quantum correction in thermodynamics equilibrium. And this one represents the probability distribution in the quantum case. And also, we can write this Wiener function in terms of the pure state this way. Okay? And this Wiener function satisfies the following properties. We have a bounded function, we also have a real valued function, and the marginality conditions are also satisfied. And when we sum up all the probabilities of our random variables q and p, this one is equal to 1. Okay. Linear functions allow us to analyze data sets, and then this one allows us to plot these data sets on phase space. In modeling of optical system, linear function is used in fiber telecommunication, and also in signal analysis. Linear function represents electrical signals. We also have mechanical vibration, and then we have sound waves. And in image analysis, they filtered this linear function in order to study the structure of a certain image. So these are some physical application of linear functions, okay, in classical and in quantum case. Okay. Wolf and co-workers extended the construction of these linear functions on Lie groups. So for the construction, we need to identify a Lie group G, and of course its element. And then you have to construct the Vial operator this way. So we have the integral over the group of the exponential times we have here the group element, and then we also need the Haar measure of the group. So these are the ingredients that we need in order to construct the linear function on Lie groups. And instead of using the group element so that this operator can act on the basis function, we're going to replace this group element by the unitary representation. Okay, and then to construct the linear function, we need to consider the inner product of the basis function in the representation space with the constructed Vial operator. Okay. And these steps or these formulations are actually applied in the case of the Heisenberg-Vial group. And they found out that the linear function on the Heisenberg-Vial group is just the same as the linear function constructed by Wiener in 1932. And thus, this one, the construction was actually extended to other Lie groups, such as in similitude group and also in affine group. Okay. And we can also see here the fundamental relation of the Vial transform and the linear function by computing the quantum expectation value. So this one is the inner product of the basis function with the Vial transform. And this one is expressed in terms of the Vial, the linear function. Okay, so what is the meaning of this quantum expectation value? This one would mean the probable location of a particle or energy on phase space. Okay, so to illustrate this, we have to consider this illustration. The red spot, which is the darkest spot in this figure, is the most probable location of a particular energy on phase space. And thus, this red mark here is equal to the quantum expectation value of that particular energy. Okay. So the next object is the star product of functions on phase space. For our motivation here, we want to look for an operation, okay, for functions on phase space that will replace the pointwise product of functions, because this one is not suitable in quantum mechanics because of uncertainty principle that says that we cannot localize points on phase space. In order to do that, we're going to formulate this time a non-commutative but associative product of functions. And we're going to call this as Grunwald-Moyal star product. Okay? And in order to formulate this or to construct this, we need the composition of two Vial transforms, and eventually this one will give us another Vial transform with symbol F star G. And this star here will represent the Grunwald-Moyal star product, or later in our discussion, we will call this as the twisted convolution. Okay? And this star has the same property as the C star algebra, which is bounded. This one is also associative. And we have here the existence of the identity function. And this one is linear. And then involution. And also we have this triviality condition. And the construction was again applied on Lie groups, specifically on the Heisenberg-Vial group, wherein Wong formulated the Vial transform in the Heisenberg-Vial group case using the Fourier transform of the function sigma and the Schrödinger representation. And also, we have here the composition of two Vial transform in order to come up with the twisted convolution. As we can see here, this star is actually the kernel of this operator. Okay, so this star now okay, is regarded as the Moyal star product, or we have here the twisted convolution of these two functions given by this equation. Okay. And we want to apply this circle of ideas on Euclidean motion group of rank 2. But before that, we want to I want to see first, okay, the concepts that we need in order to formulate this on another Lie group, which is the Euclidean motion group. Okay. So first, let's define a Lie group G. So what do we mean by this? This one is a group and also a smooth manifold. And then we also need the concept of semi-direct product of H and G. Okay. So G being a transformation group that acts on the abelian group H, and the semi-direct product of these two groups is a group P with this operation, wherein P here is equal to the Cartesian product of H and G with this group law. Okay. And we chose our Lie group to be the Euclidean motion group of rank 2, wherein this is the semi-direct product of the translation and the rotation group, or we call this as special orthogonal group. Okay, and the group elements are parameterized by, we have your small a coming from the translation group, and then capital A here coming from the rotation group. And since this one is the semi-direct product of this translation and rotation group, we're going to adapt here the group law, and this one is the inverse of this group element. And also this group can be written as a 3 by 3 homogeneous transformation matrix of this form. Okay. Next, in robotics, Euclidean motion group is actually used to illustrate the movement of a robot arm. Okay, that shows here the translation and rotation. So that's actually how the robot arm works. Okay, using we have here the Euclidean motion group. And we also have the concept of Lie algebra of a Lie group G. So this one consists of an n by n matrices such that e raised to sx is an element of G, satisfying these properties. Okay, take note that we have here a Lie bracket defined this way. Okay, and we also have the concept of exponential of square matrix, since our group elements are actually written in exponential form. Okay, and we also need the concept of exponential mapping. This one shows the connection of the Lie algebra and the Lie group G, okay, given by this mapping. And the Lie algebra of this group is spanned by the matrices R. We have T sub 1 and we have T sub 2, satisfying this Lie brackets. And if we have to consider the group elements of E2, okay, so this one is equal to the group element of the translation times we have the group element of the rotation group. Okay, and we have here now the exponential map that link the Lie algebra of E2 and the Lie group E2. Okay, so look at this. We have the group element of E2, which is now expressed in exponential form. And when we use here the exponential of a matrix, this one will result to a 3 by 3 transformation matrix, okay, given by this matrix here. Okay. And we also have the concept of unitary representation of a Lie group. This one is important so that the group can act on the basis function in the Hilbert space. So what are the properties? So we have here homomorphism property and this mapping. Okay, G to U sub GV is differentiable, and then U here is unitary. Okay, and let's consider the unitary irreducible representation of E2. Okay, so this one is equal to the unitary representation of the translation, and we have here the rotation group, wherein S here counts the number of irreducible representations. So S is an element of a real number. Okay, and this one is in L2S1, meaning that this one act on the function of a circle, and this is actually the definition. Okay, and the inner product on L2S1 is defined this way, given by this particular equation. Okay, next, we also have the concept of matrix elements of the UIRs of G. This one is obtained by getting the inner product of the basis elements with the unitary irreducible representation. Okay, so if I'm going to apply this on matrix elements of the UIRs of E2, this one will give us this particular expression involving special function, which is the cylindrical Bessel function. Okay. With the following properties. So we have here the adjoint property, homomorphism property, and this one is the orthogonality property of these matrix elements. And also, if we want to integrate over this Euclidean motion group, we need the concept of Haar measure. So this one is obtained by getting the determinant of this Jacobian matrix times we have the differentials of the parameters of G. Okay, so here is the Haar measure on E2, okay? And take note that the left and then the Haar measure of this group are actually equal, and we call this as a unimodular group. Okay. And we also have here the Fourier transform version on Euclidean motion group, wherein we have here now the Fourier transform, which is in terms of the unitary representation of the group. And also, we need the convolution of two functions on L2S2 given by this particular equation. Okay, and we are now ready to see the results. So we have here the linear function on E2. First, we formulated the Vial operator on E2. So we have here the integral over the group, okay, of the exponential of, we have here x. This is a column vector in R3 times we have here the parameters in this particular group. And we have here the group element, and we substitute here the Haar measure that we formulated a while back. And instead of using, again, the group element, we're going to substitute here the unitary irreducible representation. Okay. And in order to compute for the linear matrix on E2, we have to consider the inner product of the basis function, okay, on L2S1 with the Vial operator, and we obtain this particular expression. Okay, and to compute now the linear function on E2, this one is again equal to the inner product of the matrix elements on E2, and we obtain this expression. And here we are actually given the cylindrical Bessel function. Okay, this linear function is now expressed in terms of this special function. And we check also the properties of this. This one satisfies sesquilinearity. We also have reality condition. And then we have marginality conditions are also satisfied. And we also have here the traciality condition and covariant property. So these are the properties that the linear function that we have formulated. Okay. And we check also if the fundamental formula on the Heisenberg case is also applicable or true on E2. Okay, so we consider the inner product of the two functions in L2S1 with the Vial transform. And we found out that after expanding this, okay, this one can also be written in terms of the linear function. So this one is the fundamental formula version on E2. Okay, or this is the expectation, quantum expectation value, which is on E2 case. So we check also the star product of phase space functions on E2. So we formulated the Vial transform on E2 given by this particular equation. And we also compute for the composition of two Vial transform on E2. And we have this particular result. And we found out that the composition of two Vial transform will give us another Vial transform, but with a symbol F star L, okay, given by this particular equation. And this F star L is actually the kernel of this particular operator. And take note that whatever the properties of this operator will be inherited by the kernel. So in order to show the properties, we just work on with the Vial transform, and that will be inherited already by F star N. And we have shown that the composition of two Vial operators, okay, is bounded, and hence we can say that F star L here is an element of the Schwarz class of E2, and hence F star L here is bounded. And we also show that star here is associative, and then linearity is also satisfied. And then we also have the existence of identity function. In this case, the Dirac delta function is actually analogous to identity function 1 in the Heisenberg Vial case. Okay? And then we also have here the traciality condition. What we have seen here is that the C-star algebra properties are also observed on the star product of functions on Euclidean motion group of rank 2, just like in the Heisenberg Vial group case. Okay? And I want to share also the work or the project that we are currently working on. This one is actually has this object is actually connected to the circle of ideas that we discussed a while back. Okay, so let's recall again that uncertainty principle tells us that we cannot measure at the same time, let's say, two sets of complementary variables that may have more than one dimension on phase space. Okay, so that problem will be solved by this object called the localization operators. Okay. And we can see the application of localization operators on these three cases. We have in robotics, if we want to measure at the same time the position, and then we have orientation. And in signal analysis, if we want to measure both the time and frequency. Okay, and in image analysis, if we want to consider only portion or section of a certain image, that is actually equivalent to finding window function. So that is actually an application of localization operators. Okay, and in order to construct these localization operators, we need the concept of coherent states. Okay, so these coherent states are actually phase space, are actually linked or connected to phase space, and a natural tool in order to construct localization operators. Okay, so these coherent states are L2 functions, meaning square integrable, and this one is labeled by phase space points. Okay, so how do we construct coherent states? First of all, we need to find a fiducial vector, or what we call here the admissible vector or wavelet. Okay, so we can only find this if we have square integrable representation. So here, there exists a vector phi in the Hilbert space such that this particular expression is true. Okay, take note here that we have the action of irreducible representation with the vector in the Hilbert space. So if this one is satisfied, then phi here is called the admissible wavelet, and this u phi here is called the family of coherent states. And if you have to evaluate this integral, okay, so the value is what we call the wavelet constant associated to the admissible wavelet phi. Okay, and these coherent states are localized on phase space around the point with, let's say, coordinates QP. Okay, and the most important properties of these coherent states would now be the resolution of the identity formula. Okay, so here for all x and y elements of the representation space, this equation must be true. Okay. And also we have the concept of wavelet transform associated to the admissible wavelet phi. Okay, so this wavelet transform, okay, converts the function f in the representation space to the functional Hilbert space, which is actually inside L2G. Okay, given by this particular equation. And the resolution of the identity formula is actually linked to this wavelet transform using this particular equation. And we can actually formulate the localization operator given by this mapping we have here from representation space to another Hilbert space here, given by this equation. And we call this as the localization operator with symbol f, wherein f is a function of this space. Okay. And here are some properties of this localization operator. So if we let f to be an element of L1G, L infinity, and then LP spaces, wherein P here is greater than 1 but less than infinity, the localization operator with symbol f is actually a bounded linear operator. Okay? And they actually apply this construction in the Heisenberg-Vial group case and in the affine group. Okay. And Wong applied this on the Heisenberg-Vial group case and actually found two important results. Okay, he computed the localization operator and found out that this one is just equal to the Vial transform with symbol f star lambda. So f star lambda here is the convolution of f and lambda. Okay, and another important result is that if we have to get the product of two localization operators, say in L2CN, because our representation space is L2CN, in the case of the Heisenberg-Vial group, this one will actually result to another localization operator with symbol H. But this time, this symbol may not be in L2CN even if F and G are actually functions in L2CN. Okay, and we want to um, mimic or apply this construction on Euclidean motion group of rank 2. Okay, but the problem here is that according to Isham and Cloder, the representation on of E2 on L2S1 is not square integrable. So we need to make an adjustment in the construction that we discussed a while back. But according to the paper of Dewitz, okay, so we have here a statement saying that every non-vanishing wavelet which is an element of this space is admissible. And psi here is equal to this particular expression. Okay, and instead of using the unitary irreducible representation, we have to use the unitary representation on L2R2. And the action is given by this particular equation. Okay, and we replace the constant wavelet C sub phi in our discussion about a while back by this wavelet constant m sub psi, and we have shown that this one is actually finite. Okay, and the wavelet transform version on E2, okay, is actually has a domain which is the representation space of E2, and this one is mapped to the functional Hilbert space, which is a subset or subspace of L2 of E2. Okay, so given by this particular equation. And take note that this wavelet transform is unitary. And the resolution of identity formula, which is the version on E2, is still linked to this wavelet transform given by this particular equation. Okay. And we formulated already the localization operators on E2 given by this particular equation. And this one is called the localization operator with symbol F on E2. And we check also the properties of this. We let F1 be an element of L1G, and then F is an element of L infinity, and F is an element of L2G. And we found out that if these are the cases, then the localization operator with symbol F is bounded. But I still need to compute if whenever F is an element of LP, this time P is greater than 2 but less than infinity, we want to check if LF is still bounded. And then we want to check also if our computed localization operator is connected to the Vial transform that we computed. Okay, so that actually the end of my presentation. And I want to thank Dr. Inda and the mathematics department of Gadamada University for inviting me and for allowing me to present our work in this special event. Okay. Thank you po. And here are my references.
Thank you, Larni, for nice and beautiful explanation. Uh, Maybe there is some questions, but before I will ask something about your speak. I heard about the negative value on the distribution function. So why you consider the negative value on the distribution function? So why this is happening?
Because of quantum interference. That is actually due to quantum interference. That is the meaning of that negative probability in that quasi probability distribution.
Okay, thank you very much. So there is a question from Juanda Klana. So apologies in advance. I want to ask, how is the Wigner Wheel formalism for Lie groups? Does it apply to any Lie groups or specifically to compact Lie groups? Thank you very much.
Actually, the construction given by formulated by Wong and co-workers applied on arbitrary Lie group. So I think that will actually apply to any.
Very good. Okay, thank you very much. So any other question from the participants? You can ask directly to Lani by turn on your microphone. Okay, any other question? So so before that, I want to ask something again. So there is a concept of localization function, right? That's very important for this um, the for the formation of the star product, I think, of the function on the phase space. So what is the concept of localization function for what is it? Why this is important?
This one is important in, say, for instance, measuring at the same time two variables because that actually forbids in the quantum and in the classical case because of the uncertainty principle. But because of this localization operators, we can now measure these two variables at the same time.
Okay, thank you very much. So there is a question from Niken Prima. I'm interested in a star product of function of phase space and Lie group. Based on the property of star product, may we construct an abelian group from the function set on phase space over the star product operation such that it is a module over the ring of integer number? And the second question, what is the meaning of 2 on the notation A2? Thank you very much.
Okay, so I want to answer first the meaning of the notation
Yeah.
in ano. Okay, so E2 means we have the Euclidean motion group of rank 2. Okay, so we have in E2 we have R squared, and then in we have another group which is SO2, meaning we have here a rotation group which is in the circle. Okay, so you have two-dimensional group. And then what else? May we construct an abelian group from the function set on phase space over the star product of functions such that it is module over the ring of integer number. I'm not sure about this one. I'm not sure about this one. Sorry.
Okay, thank you, Lani. So any other questions? Another question? So I'll ask again. So you said about the application on the uh, what I had this uh, the application on the robotic and signal analysis and image analysis. So what is the, I mean, what part on your research that applied on those field? So, for example, like yeah, how to moving the robot and like that. So, in the, I think in easy way to explain it.
Actually, since we considered Euclidean motion group, wherein the parameters are we have the translation and then the rotation group. I just actually consider applications on real life applications of this Euclidean motion group, or in say for instance in robotics, and I mentioned some in image analysis, and then in what else, signal analysis. But in my research, we did not actually cover the physical application. I just mentioned it now for us to see that these objects are actually important.
Okay, thank you, Larnie. I think that's all of my question. Any other questions before we jump to the next speaker? You can ask directly to Larnie by unmute your microphone. Okay, there is no other question. Maybe after the second lecture, some participant want to ask, then I will directly ask to you. So thank you, Larnie, for the nice speech. Uh, so I will jump to the second speaker, Professor Indah. But before that, I would like to introduce Professor Indah first. So I will. Okay. So for our second speaker, Professor Dr. Indah Emilia Wijayanti. She is professor in Universitas Gadjah Mada. She got bachelor in Universitas Gadjah Mada and continued her master as well in Universitas Gadjah Mada, and finally got the PhD, a doctor in mathematics in Heinrich Heine University of Düsseldorf, Germany, with dissertation title Co-Prime Co-Modules. I think this talk will has something to do with this dissertation, and with supervision by Professor Robert Wispel. So there is two recent publication from Professor Indah. First title, The Uniqueness of Binary Operation on Semi-Locally Simply Connected topological groups. And second one titled on Class of Lambda Modules. Okay, I think that's all for Professor Indah. I would like you invite you to start the second talk. So I stop sharing this one to Professor Indah, please.
Thank you very much, Benny, for the introduction. Good morning, everyone.
Good morning.
Assalamualaikum warahmatullahi wabarakatuh. Yeah, thank you for all the committee team for this lecture series. And let me share the presentation. Can you see the slide, Benny?
Yeah, I see the slide now.
Yes, okay, thank you. Yeah, thank you very much. My talk is about what C-star algebras, a little bit of an overview or a recall some notions in C-star algebras and compact quantum semigroups. And I will connect it to some algebraic structure, that is co-algebras and comodules, and some overview of what we can do in this algebra, I mean in this module theory on ring theory. So this is the outline. Yeah. First, I will give some motivation and what is some notion in C-star algebra, some examples for it, and also the idea what happened in quantum species and their morphisms, such that we can connect it to the algebraic structures named algebras and comodules. So actually the motivation of C-star algebra comes from complex numbers. Consider C is the set of all complex numbers. We can describe these numbers. Z is equal to x plus iy. And we have also modules in these complex numbers with this formula. So the modules of z is equal to square root of x squared plus y squared. And we also have complex conjugate denoted by z star. This is the conjugate of these complex numbers. And also we have a norm in these complex numbers. And now we can consider this conjugate as a function from C to C. That is, bring all the complex number to its conjugate, yeah, and which has property like this: Z star star is equal to Z itself. Later, we can make this notion to something more abstract. First, we recall the C algebra. What is the C algebra is? Let A be a vector space over field C, over field the complex numbers, and we have this in this vector space. We can define multiplication with this notation and with these properties, distribution, and also these properties. So we can we call this A is C algebra over C. So this C algebra actually a vector space equated by a product. Note that this C can be replaced by any ring. So in a more general situation, we have R algebra, which is R is any rings. Some examples here I can mention that C, the polynomial over complex number is an example of C algebra. And moreover, a polynomial over any ring R is also R algebra. And matrix, the set of matrices over R over ring R is also the example of R algebra. So the examples here is seems familiar to us. And now how about the star? Yeah, we see from the complex numbers we have conjugate, yeah, and we can make it more abstract. We consider this star as a map from A to A itself. We call it an involution if this star satisfies these properties, this anti-linear, and A star star is equal to A itself, and AB star is equal to B star times A star. Now we come to the definition of C star algebra. The algebra A is called a star algebra if it is a C algebra with convolution. So algebra over complex number completed with involution. And this algebra is called Banach algebra if it is complete norm C algebra satisfies this formula, yeah, this condition. And this algebra A is called as Banach star algebra if it is a Banach algebra with convolution. And the algebra A is called a C star algebra if it is a Banach C star algebra and satisfies C star identity. So what is the difference between Banach star algebra and C star algebra is in this identity. If an algebra satisfies C star identity, they have better properties. Now some properties here. If we multiply x star with x equal be 0, then this x equal 0. And this involution, a function, it is a bijective function because x star star is equal to x. And also they satisfies the isometric and also with these properties. And Banach-Star algebra satisfies C-star identity if and only if it satisfies this property. If A is non-zero, is unital, then 1 star is equal to 1. And if an element is invertible, then this inverse star is equal to X star inverse. This is also some notion. We have, this is the notion of unital algebra if it is contains a unit. And if A, unital C algebra, and X an element in A, then we call X is normal if satisfies these properties, X is self-adjoint if satisfies these properties, unitary, projective, and so on. Yeah, so this is some definition of element in this algebra. Here comes some examples. H as Hilbert space and the set of compact operators on Hilbert space. This is the example of C-star algebra. And also the set of bounded linear operators on a Hilbert space, also example of C-star algebra. And moreover, the set of continuous function from X to the complex numbers, if X is a compact Hausdorff space, is also the example of C-star algebra. And we also have another example, matrices over complex number, also C-star algebra. For any T in this bounded operator of Cn on Cn, there exists a matrix A in this set such that this operator can be representation by this A. So T of V is equal to A times V for all V in this Cn. So this matrix is an C-star algebra equipped with the operator norm and the Hermitian involution. So the AS matrix and A star is equal to the matrices, which is the element, the entry is also the conjugation here. Here the other example, let X a compact space. So the space of continuous complex valued functions on X is a commutative C-star algebra with unit. The unit here is the constant function 1. And all operations are defined pointwise, like this. And so the norm, we define here subnorm, like this. Yeah, so this is also the example of C-star algebra. And as a special case, when we take X, locally compact space, and a function f, a continuous function f from X to complex number vanishes at infinity, it means if for its positive epsilon, the set X in X such that the absolute value of fx is greater than epsilon is compact. So the set of such function estimated by C0x. We will use this definition later. Yeah. So equipped with the pointwise operator operations and supremum norm, we define a previous example. Yeah, it should become this C0x is a C-star algebra. Yeah, because it is the special case from this example. So it is understood that the structure is also a C-star algebra. Okay, this is the last example. Cn also can be considered as C-star algebra. So by viewing this Cn as the set of continuous function from T to C, it is the algebra of continuous complex valued function, which is T is this set. So we see this Cn is also an example of C-star algebra. Okay, now we come to the other motivation here. It is well known that the theory of locally compact spaces is the same as the theory of commutative C-star algebra. Same here mean the in the categorical notion. So we have two categories, and these two categories are equivalent. Yeah. Maybe a little introduction here. Category is such every category have two classes. One is class of object, and the second class of morphisms. So we call here two categories. First is category of commutative sister algebra. As object, this is all the commutative sister algebra. This is the notion, the notation of this set of this class, yeah. And the other, the class of morphism. So every two objects in this category, for example, A and B, we define this set of morphism from A to B is phi, for example, from A to MB, which is phi is a non-degenerated star homomorphism for any A and B in this object of category. So what is MB? MB is here, this is multipliers of B. So what is multiplier? The definition is here. So if A is Caesar algebra, a linear operator M from A to A is called a multiplier of A if for any element in A, small a in A, yeah, that exists C in A such that for all B in A, we have this equation. So if we collect this function, we have these multipliers of A. Yeah. So the second category is a category of topology of locally compact spaces, which is the object is the locally compact Hausdorff space, and the morphism is a continuous map between two objects in this category. Between two categories, we have two functors. The first functors comes from the category of topology to the category of sister algebra, category of commutative sister algebra. Yeah, we call this category this functor is C0. It means for element for object in this category comes to C0. For example, we take this element X, so we send this X to C0 of X, which is the C0 is this C0, yeah. So if so, may I draw something here? So this is X from from topology from the category of topology. We send it to C0 X, which is this one is the element in category of commutative sister algebra. Okay. Yeah, and also we have the other functors from C-star algebra, from commutative C-star algebra. We send this element here to the topology, to the category of topology with this functor. This functor spec, yeah, this is the Gilvan spectrum functor. So you see that in some authors or in some reference, they prove that these two categories are equivalent. Yeah, but we still need to extend this commutativity in this second category to be any sister algebra if it is possible. Yeah. So in this commutative, this is equivalent, but for any sister algebra, this is still a question here. But we don't go to this direction. Yeah, we go another direction. Yeah, this is the extending. So how we can extend this? This is need some more research here. But we only concern in this. Yeah. Actually, by definition, we can define the category of sister algebra, which is the object is any sister algebra A, and the morphism is still the same definition as the previous categories. By this fact, the sister algebra, this category of commutative sister algebra is a full subcategory of sister algebra. Okay, now we come to the definition of a quantum space. Quantum space is actually an object of the category dual to the category of all Caesar algebra with morphism. The symbol of quantum space here I use in some reference here, like put X, put Y, and put E, something like this, yeah. And the corresponding Caesar algebra, we use the C0X, C0Y, C0A, and so on, yeah. So therefore, any Caesar algebra X, for example, X is equal to C0X, is thought of as the algebra of functions of a quantum space X. So this is the set of function of a quantum space X with X, yeah. And what about the more definition here? A quantum space X is compact if C0X is unital. In this case, we can we denote it without index 0, so we denote it as Cx. So a quantum space X is finite if C0X is finite dimensional. Yeah, in this case, C star algebra is unital and X is compact. Now we come to the another properties here. Consider the topological spaces X, Y, and E and a continuous map psi from X times E to Y. So we can define the maps from E to the collection of function from X to Y, continuous function, yeah. By this step, yeah. So for any element in E, we can construct a function by this definition this, yeah. So sigma psi E of X is equal to psi of X comma E, yeah, for all X in X. So this is the definition of function here, we have defined here. So if we take any map or function from X times E to Y, we always have this situation. So it means there exists a function sigma from function in X times E to Y to function from E to CXY with this definition. Yeah. So we conclude in this theorem. Yeah, the theorem actually meaning like this. Yeah, if we have three topological space X, Y, and E, such that E is locally compact. For any psi in this set, can define sigma psi as the mapping from E to CXY given by this definition. Yeah. So then sigma is a homeomorphism from C of X times E, comma Y onto C 8, C XY. Yeah. Okay, and now if we have three quantum spaces X, Y, and E, a continuous quantum family of maps X to Y labeled by E is a star homomorphism. So star homomorphism means homomorphism of Caesar algebra. Yeah, star homomorphism phi from CY to CX tensor CE. Yeah, note that this phi is contained in this set. Yeah, and what is the universal properties of CE psi? Yeah, we say that for any psi in this morphism, in the set of morphism from C of Y to C of X tensor C of E, so this psi is the quantum family of all maps X to Y labeled by E if for any quantum space D and any quantum family phi of maps from here, yeah, labeled by D, there exists a unique lambda, yeah, morphism from CE to CD, such that the diagram commutative. Yeah, it means if we have this one, this psi, and this psi is a quantum family of all maps from X to Y. It means if for any D and for any phi here, yeah, this diagram is commutative. Yeah, this is, we call it universal property of this CE psi. Okay, we have some remarks here that if we have two quantum spaces X and Y, the quantum space of all maps X to Y might not exist. So this not existence, this is the reason is because non-locally compact properties in this case. Yeah. So this is if the quantum space A of all maps from X to Y exists, and V is the quantum family of all maps from X to Y, then the pair A V is unique. So if there is exists, this is unique. Yeah. Unique means here in the sense that if there is another such pair, then this is an isomorphism from isomorphism lambda from A to A, from more A to A, such that satisfies this equation. Yeah, this is not always exist, but if it is exist, then this is unique. Yeah, it is one theorem that guarantee that is existence. So if we have two compact quantum spaces X and Y, assume that Cy is finite dimensional and Cx is finitely generated and unital, then there exists. Yeah, exists. And this C-star algebra A is unital. So the corresponding C-star algebra denoted by A, and this A is unital. Yeah. So the condition is finite dimensional here. Yeah. Okay, now we come to the definition of compact quantum space, the property or the definition here. Yeah. So if we have X a compact quantum space, we say that X a compact quantum semigroup if there exists a coassociative star homomorphism delta from Cx to Cx tensor Cx such that the following diagram commutative. What is the meaning commutativity here? The meaning is the composition maps here from ID tensor delta and delta
Kayak kami tuh kerja di Dharma Agung banyaknya aturan.
equal to the composition of
Harus begini.
delta tensor ID delta. Yeah, so the commutativity diagram here means this one. And also if we have X compact quantum space, we say that X has a unit if X admits a character epsilon of Cx satisfying this diagram. So diagram commutative means here, same as a previous, commutativity of diagram means the composition from here to here is equal to here to here. Now consider the quantum space of all maps from a finite quantum space to itself. Let M is the C of QSM. This is a quantum space C of M, where QSM is the underlying quantum space of M, which is a finite dimensional C-star algebra. The set of all maps QSM to QSM exists, and we denote the corresponding C-star algebra by A. Now let this map, yeah, phi from M to M tensor A. This is a quantum family of all maps QSM to QSM. So this is the special case of what we talked before, yeah, which is the set is special. Yeah, this is the special case we take here, such that we have here. Yeah, and let us consider the quantum family of maps from QSM to QSM labeled by QSA. So according to universal property of A phi, we have that there exists a unique delta, the isomorphism from A to A tensor A, such that the diagram commutes. Yeah, this is the very important for us, this diagram, and also the previous diagram. Yeah, we will show later. Okay, yes, before I jump to the algebra mode, yeah, this is what is we can conclude here. We have the structure like this, and also the structure like this. Yeah, this is what we will meet in algebra section. Yeah, because we have the structure we call coalgebras and comodul. But before we come to the structure, let me introduce you a little bit, yeah, about the group rings. So the group rings, this is about the structure that more general than a polynomial. Yeah, we have this G groups, and R is any ring. Yeah, so group ring construction which involves the group G with this operator, with operation star and a ring R. So T be the set of function f from G to R that are finitely non-zero. Supported is finite. Yeah, so the set of function from G to R, which is support f, is finite. And we can define addition and multiplication in this set like this. Yeah, the addition is normally addition, yeah, and the multiplication is the convolution multiplication. And we can prove that this set is a ring. So we call it group ring and denoted by RG. Another notion, we can view this RG as like this. Let F one element in RG. We can write F of H is a index X, and the group ring RS. Oh, I'm sorry, this is sub G. Yeah. RG is considered as the set of linear combination alpha from AHH. So H goes to all element in G, where AH in R and only finite number of AH are non-zero. Okay, this view, we have, for example, two element in RG. We can define this addition, and this is multiplication. Yeah, and here we can understand the structure of RG more clear. Yeah, from here. And this is the relation among G and R. Actually, this G is a subgroup of RG, and R is a subring of RG. Some example here. Let R is Z2, G is 1 and X, a finite group over multiplicative. Hence, we can have G to G. This is a ring. This is the group, and the element here is very simple. Yeah, 0, 1, X, and 1 time X. Yeah, this is a simple example of group rings. So as a remark, we can generalize the group G into any semigroup S, such that we obtain a semigroup ring R of S. Yeah. A polynomial ring as a special case here. If we take a ring R and semigroup non-zero element, yeah, non-zero integer, then RS is the polynomial ring over R, and we have this RS, the set of the combination linear of FSI, X up SI. So throughout, we denote these polynomial rings by Rx. Okay, so we come to the definition of R coalgebra. R coalgebra starts from R module C, with R linear maps delta from C to C tensor C, and also linear map epsilon from C to R. So this delta is called associative if it satisfies this identity, and the counit satisfies this identity. Yeah. So the this structure, we call it R algebra, and denoted by C, delta, and epsilon. And what is the meaning of this identity? Oh, no, sorry. Yeah, what is the meaning of delta? Delta here is send this any element in C to this form. Yeah, just from C to C in C, we send it to this form. And this diagram show us what is the meaning of co-associative. Yeah, you still remember the diagram we meet also in the previous slide. Yeah, in algebra point of view, this diagram is represent the co-associative property. Yeah, the diagram commutative means this composition from identity C tensor delta is equal to delta tensor identity of C composisi with delta. Yeah, and if we apply it to the element, we have this. Yeah, the identity. The co-unit diagram, we call co-unit diagram if this diagram is commutative, such that these composition are same. Yeah, this is the meaning when the diagrams apply to the element. Here the example. Actually, every ring R is a right and left module over itself, and we can take a trivial co-multiplication delta sub t here, send every element in R to R tensor 1. And we can take the identity map epsilon sub t, send R to R, so this small r to itself, yeah. And for any element in R, it satisfies this condition and also this condition. Yeah, this is the associativity and this is the co-unit property. Yeah. So by this delta t and epsilon t, for any ring is a coalgebra. Now we come to the second example. G semi-group or maybe group is also okay. Yeah? I think this is group is also okay. And we recall this group rings or semi-group rings. We define delta 1 from Rg to Rg tensor Rg. We send this any G to G tensor G. And the epsilon, we define this for any G goes to 1. Yeah. G here is element in G because in this semi-group ring or this group ring, the element of G is the generator of the set. Yeah. Furthermore, we can also define the second co-multiplication. So beside this delta 1, we can also define another co-multiplication, call it delta 2. For any G goes to this element, yeah, we divide into two cases. If G is equal to E, A is either identity and G, yeah? And the other is G is not equal to E. And the epsilon 2, we define like this. Yeah, both co-multiplication makes this Rg becomes coalgebras. Yeah. So it shows us that in one set, in one R module, it is possible to define two co-unit. Okay, for any R coalgebra C, it is possible to construct the set of right and left R module homomorphism. This is the set of all homomorphism from C to R, and we denote it by C star. Please don't be confused with this connotation. Maybe the notation is same C star, but this comes from another history. Yeah. So C star here is the set of homomorphism from C to R. And this C star is also an R module, and furthermore, C star is an R algebra. Yeah. So algebra over this ring. Yeah. And in this C-star, we can define a convolution product if we have two functions, two elements in this C-star. We can define this product such that this C-star is an algebra. So we call this C-star as dual algebra of C. Yeah. The relationship between C and C-star here, the co-multiplicative delta is co-associative in and only if this C-star is an associative R algebra. And C is a co-commutative if and only if C-star is commutative R algebra. And C has a co-unit if and only if this C-star has a unit. So both of them have the type, the relationship here. Now, what about the morphisms between coalgebras? If we have two coalgebras and we have R linear maps F, so this map becomes a coalgebra morphism if satisfies this commutative diagram. Again, commutativity here means the composition are same, yeah, from here, from bottom to up and the left, yeah, and this is the same as from bottom to left and then up, yeah, the same value. And if we want to see what is the implication to the element, so it is the meaning, yeah. This is the meaning of the commutativity of diagram, also for this, yeah. Okay, now we come to another structure in algebra. We call it comodules over coalgebra C. First, here we have algebra, and then any R module M with a co-associative and co-unit or right coaction is called a right C comodule if satisfies this diagram is commutative. Okay, and when the commutativity of this diagram means for all M in this is the example. Yeah, the example. Let R be ring, and we can consider this R as a trivial R coalgebra. And we have now R module M. This is, we can also
Okay, maybe there is some connection problem from Professor Indah. So we will wait for a moment. Oh, so we will wait a minute. Okay, there is Professor Indah. Okay, I think there is some problem.
The connection is,
yeah.
Okay, is now okay?
Yeah, you can continue.
Okay, thank you. I'm sorry. So it is still in my slide, or should I share once more?
Not yet share your slide.
Okay. I'm sorry.
Okay.
Okay, you can see the slide?
Looks good.
Okay, thank you. Yeah, okay, yeah. So if we have this R ring is a trivial R algebra, and for any R module M, we can consider it as a trivial comodule with this co-multiplication. Yeah. Okay, and we come to another example. Yeah. So based on the first example, now we consider this Z module over integer. This is a matrix over integer. This is a trivial commodule over this integer, yeah, by a collection like this, yeah. If we have G is monoid and R be a G graded ring with trivial grading, and R module S a G graded module, if and only if it is a commodule over this algebra. Yeah, this is also the example. Yeah, also, yeah, we have this R algebra RZ, and the module is here, and this is the algebra, and we can make the co-multiplication like this, yeah, where this is the definition. Yeah. So this is also the example of comodules over RZ. Yeah. And what is the role of C star here? Yeah, we have that every R of algebra C is a right and left C module by C coaction. Yeah, this is also a special case of comodule. So every coalgebra is actually also a comodule over itself. Yeah, and furthermore we have this property, the important property, which is the C star has important role in the structure of comodule, which is every right C commodule M is a left C star module by this action. Yeah, so you see here the action we can define from C star action to tensor M goes to M. If we have two elements here, F in C star and M in M, we can send this element to this element. Yeah, this is actually contained in this M. And also satisfies the axioms of modules. So proposition here guaranteed that every right C commodule M is a left C star module. This is a very important tool because we can transfer some properties in the conventional module to the C star module. Yeah. Again, in the commodules, we also have the morphism of commodules. This is actually the homomorphism, but with the more addition condition. Yeah, this homomorphism should satisfy this diagram, commutativity of diagram. Yeah, so beside this homomorphism, this F should satisfy this identity. Yeah. And for any M, this identity means it should be satisfies this identity. Yeah. Now, if we collect all C commodule morphism from M to N, for example, we denote it by hom CMN. This is for right commodules, yeah. And if you have a left commodule, we denote it by this one. What is the different left and right commodule? It depends on the position of the C. So we define right commodule when C is in the right side. On the other hand, we have the left commodule if the C in the left side. Yeah. Moreover, for any dimorphism H from M to N in this category of commodule is a left C star module morphism. Yeah, it means if you have if you take any morphism in this set, it should be contained in this set. Yeah, but not the converse. Yeah, the converse. So the question is here when these two sets are same. Yeah. Yeah. So this is one of answer for the question that we define here alpha condition. Yeah, alpha condition said that if the alpha condition goes to this coalgebra, yeah, coalgebra C is set to satisfy the alpha condition if this map is injective. for every n in M. So with this condition, we have the proposition that if the coalgebra satisfies the alpha condition, so the homomorphism, both homomorphism will be the same. Yeah, will be the same. But without alpha condition, only subset. What is the meaning if the homomorphism are the same? So what is the meaning if it is the same? It means we have a subcategory of, I'm sorry. Yeah, we have this category, the category of comodules is a subcategory, a full subcategory of module of C star. Yeah. If it is not satisfied, it is only the subset. But if it is yeah. Okay, for the last slide here, I show some observation of algebras and comodules. So after we get the structure of algebras and comodule here, we can do many things in the sense of algebra, yeah, in the sense of algebra, ring theory or module theory. We forget about the topological or compactness, yeah, properties. We only concern in the structure of algebra. So you can treat this algebra and comodule as an object in the algebra. Yeah, for example, we can define something. For example, here the property of clean. We meet this property in the classical and the conventional module theory, but with the bridge of a C star module, yeah, we can bring this property come to comodules and coalgebra also. This is one example. And also, for example, here the notion of fully coprime, yeah, and fully coprime here we meet this notion in module theory, but now we can bring it to the comodules and coalgebra theory. Yeah, so I think this is one example. Beside 7 examples here, there are many examples of observation of algebras and comodules. This is the reference. Yeah. And this is our research group, C star algebra. I'm sorry, I don't have the normal picture because we start the discussion in this group during the pandemic, so we don't have the normal picture. This is only a online picture. And special thanks to Juanda Kelana Putra here, and also Nikan Prima Puspita, you also here. Special thanks to colleagues in C star algebra research group for the fruitful discussion. Thank you for your attention. Thank you very much, Benny.
Okay, thank you very much, Professor Indah, for a wonderful talk. So yeah, there is so many abstract things here in your talk. There is a question here from Juanda Klana. So the definition of compact quantum semigroup is adapted from the definition of coalgebra. Similarly, we can adapt the quantum structure of comodule. Is there any possibility that we can adapt the quantum structure of B algebra and Hopf algebra? Thank you very much, Professor Indah.
Yes, I think we can do it in a very complicated way, I think, yeah. Because B algebra or Hopf algebra, we mix together the structure of algebra and coalgebra and the same set. Ya kan? So the set we can consider it as algebra, and the other hand it is also algebra. So in the times algebra. So if you will mix this notion to the quantum semigroups notion, I think maybe it can, but in a very complicated way, I think. Okay, you can hear me?
Okay.
Hello?
Yeah, thank you very much, Professor Indah. Any other question? You can directly ask Professor Indah by unmute your microphone.
Yeah, please.
Maybe I will ask something. So this is this new concept to abstract the property of C-star algebra to the modules or the category of C-star algebra, or this is I think has been derived a long time ago, and you just add something on this.
Yeah, okay. I think the structure of coalgebras and comodules in 1960s somewhere, something in 1960s or maybe 1970s. Yeah, Switzerland, I think, the first person introduced this structure. In the time, the structure is still vector space. Yeah, so vector space, you can dualize it as a phi goes to phi tensor phi. Yeah, and in 2003, maybe, yeah, 2000 something, Wisbauer and Brzezinski introduced the coalgebra of a ring. So they involved modules here. And after that, after we can bring a module becomes a coalgebra, then many algebraists who works in module theory try to transfer some notion and modules comes to the comodules or coalgebra. So maybe 2000 something, yeah, the observation of coalgebras and comodules of a ring becomes very high, yeah. And what we do, what's our contribution? For example, we define the primes. My last research, yeah, we brings the primeness in modules comes to comodules. And what is this year do by my students, Nikan, yeah, she brings the cleanness of modules from modules theory to the comodules, clean comodules in comodules thing. Yeah, maybe this is some example. Yeah, how we can we still continue observe these structures.
Okay, thank you, Professor Indah. Is there any other questions from participants?
Maybe my comment, Benny.
Yeah.
What is my question is, after we saw that the structure of coalgebras and comodules come to quantum semigroups or quantum groups, how we can bring back what is our result in algebra, bring back to the functional analysis. This is my question actually. How? Ya kan? After we observe many things. Yeah.
Because you get rid of
how
the space, I mean the functional space. So how to make it to make it back space, right? Yeah, because if I study the C-star algebra, we have the polynomial algebra. Also, this is something to do with the dual space. So if you get rid the space, and then how to reconstruct the space.
Yeah. This is the question.
Thank you very much for the nice talk. I think there is no other questions. So I would like to remind you that we have a photo session after this talk. Thank you very much, Professor Indah. So now we come to the photo session. Please turn on your camera. So we have, I will take the screenshot. Can you stand still for a big smile and for a moment? This way to, okay, thank you. That's all the photo session. Thank you for joining the photo session. I also remind you to fill the attendance form that I put in the chat column. Then you can fill it using the following link. Now we invited Professor Indah as the organizing committee to give the announcement for the next lecture. To Professor Indah, please.
Okay, thank you very much, Mas Benny, for to be this host here today, moderator. All participants, thank you very much, and also for Dr. Larni, yeah, thank you very much for your talk today. And we still have one lecture series in the next August. In the 21st August, yeah, we will have this lecture, the third lecture series. And please come again, join us again. Such that we have all the series completely. Yeah. Thank you very much for the committees, also for the participants, and also all the speakers for the 3 lectures. Thank you very much.
Yes, thank you very much, Professor Indah. So I would like to remind you that we have in total 3 programs of lecture series. The last one will be on 21st August 2021. Keep in touch and come join the lecture. We will inform you the following events soon. That's all our agenda today. Thank you for joining us and see you on the next lecture. Bye. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Bye, everybody.
Waalaikumsalam.
Bye.
Thank you very much, Ben.
Thank you very much.
Terima kasih. Thank you very much.
Hostnya ini ya, Mas Jilan ya.
Mas Jilan.
So feel free to exit if you wish to.
Okay, maybe.
Ya, izin ya, Benny.